Today we will be studying one interesting function which is known as characteristic function, that is associated with a random variable. Now we know that a random variable, whenever there is a random variable, we can think of a distribution function. In most of the situations, we can also think of moment generating function. That means that generate function that generates the moments of that random variable or the distribution of that random variable, provided obviously the moments exist. Now a similar concept, but a very important one, that is known as characteristic function, which in some sense characterizes a distribution. Now we will be studying what is the meaning that in some sense it characterizes a distribution, or what is the usefulness of studying such a function. Now remember, characteristic function, at least as it is defined, usually is a complex valued function. So we will be studying, first we will define what is the meaning of characteristic function, how it is defined. We will see why, at the very outset, why do we need this characteristic function when we already have a distribution function or a PDF or a PMF of a random variable. There might be some theorems that actually shows some properties or studies some properties of this characteristic function, which will be eventually useful in studying the distribution. So we will be studying some properties and some theorems related to characteristic function. Characteristic function 1. As discussed just now, let us note some interesting things, that it is possible for a random variable that we cannot get the PMF or probability mass function, neither we can get PDF or probability density function. But in any random variable, whatever be the situation, whether PMF exists or does not exist, whether PDF exists or does not exist, does not matter, but the distribution function always exists. So distribution function is basically a very unique way to represent a probability distribution of a random variable. So naturally, if we know the distribution function, we would be able to know everything about the probability distribution of the random variable, although we may not know the PMF or PDF, that is probability mass function or a probability density function. Because as we know that PMF exists only when the random variable is purely discrete, and PDF exists when the random variable is absolutely continuous in nature. Now the question is, now another important feature is that feature for a random variable or the distribution of a random variable, that is some characterizations of the distribution, that is in terms of the moments. So we can define moments of a random variable in a very standard manner, we all know that. But the problem is sometimes moments may not exist, that or sometimes moments may exist up to a certain order, say up to second or third order, but beyond that moments may not exist. Another very troubling feature is a troubling scenario that is observed, that moments may not uniquely determine the distribution function. That means we might get the two entirely different distributions, but with exactly the same moments. So the question is, moment generating function, since moment generating function may fail to characterize a distribution, that means because we always usually our common perception is that whenever there is a distribution we can go and calculate the moments, but sometimes moments may not exist or moments may not uniquely determine a distribution. So in such a case, if we even define moment generating function, that means a function that generates moments, but it may fail to characterize a distribution. That means if we have a sequence of moments, we may not get the distribution uniquely, or if sometimes moments does not exist, then naturally the question of considering moment generating function will not arise at all. So here comes a most important question, is there anything that will characterize a distribution in some sense uniquely? So, this is the question, that can we characterize a distribution function uniquely? Fortunately, the answer is yes, and to clarify this answer, we need to introduce one interesting function, which is nothing but characteristic function. So, first we will define this characteristic function of a random variable or characteristic function associated with the distribution function of a random variable. The definition is very simple. So, the characteristic function is of a random variable with distribution function capital F x is defined as phi t. This is denoted by phi t, which is a function of t. T is a real variable and is given by expectation of e to the power I t into capital X. Capital X is a random variable. So, naturally according to the definition of expectation, this is minus infinity to infinity integral of e to the power I t x d f x. Since we know that e to the power I t x can be written as cos t x plus I sin t x, we can just split this integral in the form of expectation of e to the power I t x equals to integration minus infinity to infinity e to the power I t x d f x equals to integration minus infinity to infinity cos t x d f x plus I times minus infinity to infinity integral of sin t x d f x. Just put this e to the power I t x equals to cos t x plus I sin d x and we will get this result. So, this entire thing can be treated as the definition of a characteristic function of a random variable x whose distribution function is given by capital F x. So, let us consider some properties in the form of a theorem. First theorem is phi of 0 equals to 1. That means, when t equals to 0, phi 0 is 1, whatever be the random variable and whatever be the distribution function. Proof is extremely simple. Just put phi 0 means e to the power phi 0 means t equals to 0. So, e to the power I t x is just 1. So, integration minus infinity to infinity d f x. So, e to the power I t x is 1, d f x. If we integrate this becomes capital F of infinity minus capital F of minus infinity. Now, capital F is a distribution function. So, capital F of infinity, if you recall the properties of a distribution function, so there are 3 properties and we are using one of them, which is capital F of infinity is 1 and capital F of minus infinity equals to 0. So, this entire expression becomes equals to 1. Now, note that this value is 1 irrespective of the form of the capital F, that is form of the distribution. So, as long as capital F represents the distribution, this is fine, this property will hold. So, phi 0 is 1 irrespective of any distribution function. This is very, very interesting result, that mod of phi t less than equals to 1. That means, this characteristic function, this is a function of t, whatever be the random variable, whatever be the distribution function, the characteristic function corresponding to this random variable and the distribution function is always bounded by 1. This is very interesting, that the value is just 1. So, proof is extremely again simple. Capital mod of phi t less than equals to, just we can write this as mod in integration minus infinity to infinity mod of e to the power I t x. So, we just bring this mod sign inside the integral sign and hence this inequality. And we know what is the modulus of e to the power I t x. So, e to the power I t x modulus of that is square root of cos square t x plus sin square t x, which is equals to 1 whatever be the value of x and t. So, this becomes 1 and hence again minus infinity to infinity d capital F x, which is nothing but capital F of infinity minus capital F of minus infinity, which is equals to 1. The C is, I have already mentioned that small phi t is generally a complex valued function, because it is expectation of e to the power I t x. So, if we consider phi of minus t, that means we evaluate this function phi at, instead of t, if we put minus t, then this is nothing but the complex conjugate of phi t. So, if we just write this expression, we will immediately see that phi of minus t nothing but the complex conjugate of small phi t, that is phi bar t. So, these are the three very basic properties of a characteristic function. Another theorem which states that every characteristic function, that means I am not worried about what is the nature of distribution function that is considered here. Irrespective of any distribution function, the characteristic function of that random variable for which there is a distribution function is, say, capital F, is always uniformly continuous on the real line. So, over the entire real line, characteristic function is uniformly continuous. Again, the proof is simple. Just consider phi of t plus h minus phi t mod of that. Again, just using the trick that is used in proving the previous theorem, that we put this modulus sign inside, we bring this modulus sign inside the integral, and hence we get an inequality. So, this becomes minus infinity to infinity modulus of e to the power I t plus h x minus e to the power I t x into d f x. So, this integral is with respect to capital F x, which is a distribution function. Now, note that I am not considered any particular form of this capital F, except that it is a distribution function of a random variable having the three previously mentioned properties. So, this becomes, if we just take e to the power I t x common, so this becomes modulus of e to the power I t x into e to the power I h x minus 1, and modulus of e to the power I t x we have already seen is equals to 1. So, this becomes equals to integration minus infinity to infinity modulus of e to the power I h x minus 1 into d f x. Now, this quantity we can immediately write less than equals to modulus of e to the power I h x plus modulus of 1. Now, again modulus of e to the power I h s is less than equals to 1, is exactly equals to 1, this is the modulus of e to the power I h x. So, 1 plus 1 equals to 2. So, this thing is less than equals to 2, because modulus of e to the power I h x minus 1, that is modulus of a minus b, is less than equals to modulus of a plus modulus of b. And then again integral 0 minus infinity to infinity d f x is exactly equals to 1, we have just seen. So, this entire quantity is bounded by 2. Now, we just apply dominated convergence theorem, because this function is dominated by another function. So, by using dominated convergence theorem, or in short DCT, we have minus infinity to infinity e to the power I h x minus 1 d f x goes to 0 as h goes to 0. So, after a little bit of manipulation and noting the fact that this is completely independent of x and t and h, x and t rather, for every h goes to 0, this is uniformly continuous on the real line. So, this is just an outline of the proof, you will definitely get the detailed proof. Next theorem is, suppose phi 1 t, phi 2 t and so on are characteristic functions, and a1, a2 etc. are non-negative real numbers, such that summation of ai equals to 1, then summation of ai phi I t sum over I is also a characteristic function. That means a convex combination. So, when I say that ai's are non-negative real numbers and summation of ai equals to 1, that means we are considering a convex combination of characteristic functions phi 1 t, phi 2 t and so on. So, any convex combination of characteristic functions is also a characteristic function. Proof is again simple. If you consider a convex combination of the distribution functions, that means summation a j f j x, which is denoted by, say, let's call it capital X, capital F of x. So, this is a distribution function because it is a convex combination. Therefore, integration minus infinity to infinity e to the power I t x d f x, if we just put f x as summation a j f j x, then just changing the order of integral and summation, we can get in summation a j integration minus infinity to infinity to the power I t x d f j x, and this quantity is nothing but phi j x. So, summation over j a j phi j x phi j t is also a characteristic function. In fact, this is the characteristic function of f x, which is given by summation a j f j x. So, we see that from here we have observed that any characteristic function irrespective of the distribution function is always uniformly continuous, and if we have a bunch of characteristic functions and if we take a convex combination of those characteristic function, the resultant function, which is nothing but a convex combination of the characteristic functions, is also a characteristic function. That means, there exists a random variable and there exists a distribution function for which we can have this convex combination as a characteristic function. A small couple of notes: if capital F is a distribution function and a greater than equals to 0 or b is a real line, b belongs to real line, then g x equals to capital F of x minus a pi b is the distribution function of the random variable y equals to a plus b x. In fact, this is actually true for any a. If a belongs to any number in the real line, this will also hold. So, which is, and this characteristic function of this random variable y is given by g t, which is e to the power I t a into phi of b t. So, if we just calculate the expectation of e to the power I t y, which is nothing but the characteristic function of y, you see we can immediately write that expectation of e to the power I into a plus b x, and if we just expand that, we will get e to the power I t a into expectation of e to the power I b t x. So, if we replace t by b t, and this is nothing but the characteristic function of x, only t is replaced by b t. So, this function can be treated as the characteristic function. In fact, it is the characteristic function corresponding to this new random variable, which is just obtained by shifting origin and scale from the old variable, that is capital X. If we put b equals to minus 1 and a equals to 0, then g t becomes phi of minus t, because a 0 means e to the power 0 is 1 and phi of minus t, which is nothing but, as we have already seen, that phi of minus t is nothing but phi t bar, that is complex conjugate of phi t. So, naturally, and from here, if we put a equals to 0 and b equals to minus 1, y becomes minus x. So, g t equals to phi of minus t is the characteristic function of minus x, which is incidentally the complex conjugate of phi t, which is the characteristic function of x. So, from here we can get a definition that if x and minus x have the same distribution function, that means say capital F of x equals to 1 minus capital F of minus x, then we call x as a symmetric random variable, or the distribution function capital F is symmetric about origin, that is about 0. So, this is the way we can define a symmetric random variable, and the relation between the characteristic functions of this x and minus x is already given by this. Some more theorems. I am not going to give you the proof in detail, but these are some important theorems. A distribution function is symmetric if its characteristic function is real and even. Let us say it is an even function and it is a real valued function. If phi t is real, suppose the characteristic function is real, then that means phi t equals to phi bar t. This is just by the complex number results, and this is incidentally equals to phi of minus t. So, that means if x and minus x have the same characteristic function, they have the same distribution function, and hence f is capital F, that is the distribution function is symmetric. This is obtained by the uniqueness theorem of characteristic function, which we will discuss later, and this theorem is nothing but the converse of this theorem. Another interesting question that we can ask: is it possible to say something about the sum of two independent variables, or in particular if x and y are two independent symmetric variable, then x plus y is also symmetric. This result is due to Levy in 1937. So, this is actually proved, this can be proved using convolution theorem, which we will discuss. So far, we have studied something about characteristic function. So, in this class, we have defined characteristic function corresponding to a random variable or a distribution function, how it is related to the distribution function, some theorems that explains the properties of this characteristic function. Among these properties, one important property is that characteristic function is uniformly continuous on the real line. Then again, how one can define a symmetric random variable or a random variable having a symmetric distribution, and that can be explained through a characteristic function. So, this theorems or actually demonstrates some properties of this characteristic function, which will be used eventually in understanding or in deriving many theorems in this area. These theorems will help us to prove or to derive some interesting limit theorems corresponding that is associated with these random variables or the sequence of functions, the sequence of distribution functions and so on. We will discuss them eventually.